All right, thank you very much. Yeah, it's after lunch, everyone's good and awake, so let's take a trip into the solar system. What's this? This is the sun and a very, very small Mercury. Yeah, Mercury is pretty tiny, and we don't know how to make it tiny, so there are no answers in this talk, just open questions that hopefully people in this room can solve. So Mercury is a big puzzle, and it's been a big puzzle for a long time. There's a lot of things about Mercury that seem to be huge contradictions, and this all kind of took shape in the 70s with the Mariner 10 flybys. So what was the kind of biggest results that kind of sculpted the early formation models of Mercury that we're still trying to get to work now, and they're still not working? Well, Mercury has the largest uncompressed density of all the planets in the solar system. So if you take their best constraints on like J2 from the Mariner flybys, the early estimates on the physical size of Mercury's core is like 60% the mass of the planet in its core. We've refined that since. Mariner also discovered that Mercury has a magnetic field. So it potentially has a molten portion of its core. Mariner also did not detect iron oxide. The spectra from Mariner and the spectra, from observations going through the 80s and 90s, they looked a lot like the moon. It looked like something with a north acidic crust, right? It wasn't until the early 2000s that we even definitively, unambiguously detected iron oxide on Mercury. So it's a very low concentration of iron oxide. And Mercury has this thin little atmosphere that we're getting to Messenger, that Mariner detected helium unambiguously, and then subsequent ground-based campaigns identified some volatile elements or moderately volatile elements like sodium and potassium. So yeah, what's going on? This is this big mix of contradictions. So the kind of early formation models, you might have heard a couple of these, and we're still trying to get these things to work now. The one that everyone's heard about the most is probably the giant impact model, as shown in this very, very high budget animation, right? Yeah, it's after lunch. Let's all wake up. So yeah, you have like something that looked more like the Earth that has a core mass fraction of more like 30%, and then something hits it and it blows off all its mantle, and then you got Mercury left there at the end, right? So this explains some stuff. It explains that, high bulk density. It doesn't explain that iron oxide, and it also predicts like, Mercury should be super volatile depleted, which we already have these early signs that it might not be, right? So the canonical model for this is Mercury is the big guy in this. It's something like the mass of Mars and gets hit by something like the mass of the moon at a pretty booking it velocity, right? Like 30 kilometers per second, 6 times the escape velocity to do this in one impact. That's kind of hard to do. We're going to get to that in a little bit. But there's another potential scenario too, right? Mercury could be the smaller object in this encounter, right? So you can have Mercury with a mass of like a quarter Earth mass or so striking Earth or Venus at, again, a really, really moving it velocity as far as it goes, as far as relative velocities in terrestrial planet formation go, and you can, have basically a hit and run impact where you finish with 2 objects, one that's kind of like Venus or Earth, and one that's kind of like Mercury, that it's lost its most of its mantle, right? The other option too is that, well, Mercury accreted somewhere different than all the other planets, right? It accreted somewhere really, really hot, where it was too hot for all that iron to oxidize, and that explains that low FeO and potentially the high bulk density. So this is, you sometimes see this referred to as like a more of an orderly explanation for Mercury's origin instead of like a chaotic one with the impact. So there's been a lot of work on this, kind of building on this sort of a model in the last 10 or 20 years. Again, it maybe doesn't get all the flashy coverage that the impact stuff does, but this can still work too, right? So there's lots of mechanisms. Some of them have even been alluded to in previous talks in this conference, or in some posters out there. There's lots of different mechanisms to make iron-rich planetesimals, preferentially closer to the sun, that would then go in and be incorporated into Mercury and make this iron-rich planet. People proposed the photophoretic effect, where you have non-isotropic radiation on these small particles, and it can kind of size sort them, and then you preferentially form, these iron aggregates, and preferentially form iron planetesimals. You can also do it with large magnetic fields, where you can preferentially, clump together. These are like laboratory experiments where in the magnetic field, right, you're making longer little chains of irons. You've also, some of you might have seen this Johansen and Dorn paper a few years ago that was more targeted towards supermercuries, but their argument is that in supersaturated conditions, little irons nucleate inhomogeneously, and you can preferentially get dispositional growth and grow these larger little irons, and then make these like iron planetesimals. Like, okay. Also, there's this paper by Denton-Empel and Connell Alexander from 2011, where they took interplanetary dust particles, and in like super carbon-rich environments, they were able to produce these little condensates that had iron silicate ratios of about half that of our best estimates for bulk mercury. So there's other ideas out there that don't require this impact. They just we preferentially form some planetesimals that are really, really iron rich, and then mercury forms from there. There's a lot of other problems with this that we're going to get into. And then there's been a whole other array of models in the post-Mariner decades until we got to MESSENGER. People were arguing that it should be super volatile rich. There were arguments that, well, it's just this like little stray planetesimal from the asteroid belt. And so yeah, where are we at now in the aftermath of MESSENGER? Well, you might have heard the biggest thing to come out of MESSENGER is that Mercury is not depleted in volatiles. It's anything but, right? So MESSENGER detected hydrogen, water ice in the permanently shadowed regions. Mercury has moderately volatile abundances that are in excess of that of the moon. The potassium-thorium ratio, because potassium is moderately volatile and thorium is refractory and lithophile. This is like a common proxy that's used to infer a planet's bulk of volatile composition, right? So we only have the surface from MESSENGER, so we use some arguments to get into the bulk planet. The potassium-thorium ratio at Mercury is the highest of all the planets of the inner solar system. So people argued, okay, well maybe all the thorium's like segregated into the core, but another ratio that's commonly used is the chlorine-potassium ratio, also one of the highest in the inner solar system. So there's all these things pointing to like Mercury is not volatile depleted at all. Yet when you look at it, the major element composition of Mercury that we got from MESSENGER, it's super like something like an enstantite chondrite, right? It's like something that formed in these super reducing conditions. So again, we have like all these contradictions, right, that we have to be able to explain with the formation model. And then, with updated gravity data, we've been able to refine the estimate for the physical size of Mercury's core up, right? It's more like 70 to 80% with our best estimates from MESSENGER. So where did this thing come from? How do you form a Mercury? Well, you do it with planetesimals and maybe pebbles, and yeah, this is a nice little figure that I stole from Sean Raymond right here. This is rocky planet formation in one plot. We've kind of, throughout the conference talked about, these different regions of planet formation. We're going to focus in this talk mostly on the giant impact phase, but, as I've alluded to, what went on with Mercury, it could have happened earlier too. So if you do this kind of classic late stage giant impact simulation that people like Sean, John Chambers, Andre, people have been doing for 20, 30 years, you lay down like a minimum mass solar nebula, you lay down some planetesimals and embryos, and you can tweak stuff and the answer is almost always still the same. You kind of can grow 4 planets like where our 4 planets are today, but, the system itself, it doesn't look like our 4 planets today, right? This thing likes to grow big Mercuries, not, Mercury is like 0.05 Earth masses. This grows like a half Earth mass Mercury in this simulation. It also grows Marses that are too big. It also grows planets in the asteroid belt. Here's one slide resolving those last two things. This is not the point of this talk. There's a lot of text on this, but you know, if you want to pull my slides to read this, you can. We have people that have been working on the small Mars and the asteroid belt problem for 20 years now. We have lots of solutions to these things. We do not have a lot of solutions for Mercury, so that's more the point of this talk. But we have many, many different mechanisms. You might have heard of some of these, like the Grand TAC, right? Some of these things might have been polluting your archive feed over the years. There's lots and lots of models out there to make a small Mars, not so much for Mercury. We also have a lot of evidence now that's kind of pointing towards the asteroid belt never was supermassive to begin with. I've listed off a few of them here, but you know, one of the more convincing kind of came from a recent paper by Ruggiero Diano that, you know, if you look at accretion in the asteroid belt, the things that could have accreted in the asteroid belt, the biggest one that we have is Vesta. All right, Vesta's not that big. We only have one of them. If you let the asteroid belt start with more than, you know, 10 to the minus 3 Earth masses, you grow more Vestas than you can get rid of. So there's a lot of signs that the asteroid belt was small to begin with. That kind of solves that. Lots of resolutions to the small Mars problem, but not so much for Mercury. So when we do these late-stage accretion simulations, what constraints are we failing to meet for Mercury? So if you know you're tired, you're going to fall asleep after this. Is one slide. I'll give the conclusions up front. The different constraints that we apply on terrestrial planet formations, I've gone and graded, you know, to everyone in the field, myself, everyone's papers on these different constraints, right? So we want to make Mercury small. I give us a C- here, right? Mercury, the mass ratio between Mercury and Venus is like 15, right? That's pretty extreme. I mean, those of you who do like, you know, super Earth formation, you don't like grow two planets next to each other that one of them is like 15 times the size of the other one. It's also way out there on its own. I give this one a D-, or D+, sorry. The Mercury sits out there at an orbital period spacing from Venus of 2.6, right? We've talked about breaking of chain stuff, you know, today. Like, an orbital period ratio of 2.6 typically means something happened, right? So, you know, maybe something did happen. Maybe there was an impact or whatever, but this does not just come out of those, you know, late-stage accretion simulations like the video that I just showed. You also have to explain its core. Like I said, I give us a C+ here, a little bit better than the small thing, but not as good as, you know, it's dynamically excited. This is a constraint that you see applied to. Mercury has the largest eccentricity and inclination in the solar system. This is actually not that hard to do. It kind of wants to get there. This is mostly related to giant planet evolution and kind of where Mercury sits with respect to some resonance in the solar system that we'll talk about, but pretty much all the models can do this. But the other three, the jury's still out. So, you know, if you've got ideas, please tell me, because I'm out of them. All right, but you know, we're just scratching the surface, right? We can't even meet those things, but like I alluded to already, we have more information, you know, post-messenger, right? We have a lot more constraints on Mercury's composition. We have constraints on its accretion history, where it could have formed. Like, this is the stuff going forward into the future that we need to be building into these models as well. Because, you know, the current models, you know, for terrestrial planet formation, we're applying this level of stuff to like Mars and Earth too. We're going down to the chemical level constraints. We're not even there at Mercury yet. We're just trying to make the thing small. So let's take a tour through the literature. Let's take a tour through the literature of failing to meet all these constraints, right? So that first video that I showed, that's kind of the classic accretion simulation. I did 100 of these with just the classic Sean Raymond style initial conditions. And what did I do? Then I plotted up any system that like formed exactly 2 planets like around where Mercury and Venus are, right? And there were, out of 100, there were like 5, right? And so I'm plotting the orbital period ratio between that Mercury and that Venus and the mass ratio on the y-axis, and the red star is the solar system value. So obviously that just, you let the minimum mass solar nebula do its thing. As you saw in that video, you do not get a Mercury. Typically you just get like 1 Venus. You don't even form a Mercury, but if you put enough mass in, you know, towards 0.5, 0.4 AU, then you'll get like 2 little mini Venuses often. But yeah, it doesn't work. So there was a lot of talk, like when I was in grad school, everyone kind of thought that like, well, if we can just build collisional fragmentation in these n-body models that we use, it's just going to solve this, right? The collisional velocities should be faster by Mercury. We just put it in the code. It's going to start giving you some small Mercuries. It'll fix the core mass fraction thing. But it's just not efficient enough near Mercury. So this is the same, like another 100 simulations. Now we're taking, again, the Mercury-Venus systems that come out of it. But now we're using like a model that includes collisional fragmentation. And yeah, you form more small Mercuries. Again, collisional fragmentation is useful near Mercury, but it's simply not useful enough. And you also got to get rid of the fragments and the debris that you kick off too, and that's hard to do. Typically that stuff kind of gets reaccreted, and so it's like a second order effect, right? This is, just taken at first glance. This is not an instant solution to this. We've also heard talk about planet formation from rings in this conference so far. So there's a lot of these different terrestrial planet formation models that they solve the small Mars problem by concentrating the mass of the terrestrial disk in a narrow region. And it turns out that the mechanism where you kind of concentrate everything in and Mars sort of is this thing that gets kicked out, it works on the other end too. You can also kind of kick out a Mercury. So this is a bunch of different papers kind of with similar sorts of ideas. There's some Grand Tax stuff in here. There's some of Andre's simulations in here. And this will make a small Mars, right? You can concentrate the disk and kick out a small little guy and get a small Mercury. So you see we're starting to populate up on this graph, but we're not populating to the right. It is still really hard to get that orbital period spacing. This is telling us something happened. So what could have happened? Well, the first obvious thing is the solar system's instability, right? There's a whole bunch of resonances that all kick their way across the inner solar system. So what if we do this terrestrial planet formation thing while the orbital instability in the outer solar system is happening? And yeah, that can really mess stuff up, right? So now these are all the pink points, and this process is super chaotic. I've talked about this a little bit in a few subsequent slides. But now we can, if you let the outer solar system evolve and let all these resonances, move their way through the inner solar system, you can kick Mercury, all the way past this plot. You can kick it off the plot. But it's super chaotic, and it's hard to get this to work consistently. So you say, okay, well, what if, what about something like this? I won't talk about this too much, but what if we just kind of fine-tune the disk? Well, this doesn't really work either. There's been several papers, in the last 10 years or so that tried to kind of sculpt the inner disk, so it's the surface density is kind of declining, and then maybe you get Mercury to form small, space from Venus. It's really hard to get this to work. More on this later. So what now? That's the last, 20 years of literature. How do we move forward here? Well, to me, this is not solved. This is still kind of the state of things, but this is what we need to do, and this is what I've been working on and others as well. We need to figure out a way to get these, Mercury-forming giant impacts that are predicted in these, canonical giant impact models to occur more commonly in the simulations, right? That just, you do the fragmentation model in the n-body code, that they don't happen that common. Or we need to figure out what shape of the disk actually gives us a Mercury, and then we need to go from there. So I'll talk about kind of both of those things. I'll talk about the giant impact thing first, okay? And then I'll talk about the shape of the disk thing. So one of the biggest, known problems with that giant impact hypothesis is reaccretion of debris. Most of this stuff should be in dust or small objects, and the vast majority of it, after these giant impacts to erode Mercury's mantle, falls back down onto the planet eventually. There's mechanisms out there, solar wind, Yarkovsky drift, to get rid of this stuff. But that has its problems too, right? You don't want to dump too much stuff onto Venus. You don't want to dump too much stuff out to Earth and Venus late. There's other constraints here as well, even if you're able to get rid of the material. But I think the biggest problem, as we kind of alluded to, is that it's just hard to get energetic enough impacts, right? So what's this plot showing? I just took Mercury in an n-body simulation. I just kind of moved it around. Someone told me, I showed this a couple months ago. They're like, aren't the red areas the more chaotic regions? I guess they should be. I chose blue, but the blue is bad. The blue is where things get really unstable. This is just the change in eccentricity of Mercury if you move it around. And this region where Mercury lives is overlaid by a whole bunch of resonances with the giant planets. In particular, the most important one is that one that it sits on top of, which is the Nu 5 resonance with Jupiter's eccentricity. And it just sits on this like quasi-stable island next to that resonance and some other resonances with Venus. But you see like the changes in eccentricity here that you get by moving just Mercury around are like 0.2. If you look at what eccentricity or inclination you need to get a 30 kilometer per second impact, 0.2 is not going to get you there. It's not even going to get you close, right? You need like 0.8 or like an inclination of like 50, 60 degrees to get these crazy impact velocities. And even if you somehow are able to produce that, I mean, we use these orbits that are going to give you the right impact velocity. If you have something the size of Mercury, you know, in the Mercury hitting Venus thing, you have like a 0.25 Earth mass Mercury flying through the solar system like that, you're going to overexcite the eccentricities of the other terrestrial planets. So this is the angular momentum deficit of the inner solar system as a proxy for the excitation of the inner planets. We did a whole bunch of these, and you see like the red line is the solar system all the time. You know, if you have one of these energetic impacts, you overexcite the thing. So what's the solution to all this? You need a whole bunch of smaller impacts, right? So here we're just showing 5 little Mercuries. Again, you know, they're in that little chaotic region of the solar system. You're getting eccentricity excitation up to like 0.2 or so, and yeah, they can hit each other. You'll see they'll collide. They'll kick out some like little green fragments as they collide. But you can get lots and lots of impacts that are lower velocity. You can erode Mercury's mantle a little bit at a time. And so here, you know, we did a whole bunch of these, plotting the core mass fractions that you get out of them. Yeah, you can get up pretty regularly to like 0.6, 0.7. This is just a toy model, but it's to demonstrate, you know, you have a whole bunch of smaller impacts, and you can increase Mercury's core mass fraction, and you can do it without overexciting the terrestrial planets. So that's the AMD again, and you're showing an evolution here on the right where, you know, the gold and blue Earth and Venus aren't getting disrupted. So, you know, the biggest problem here still is that dynamical isolation thing, right? You can make it small, you can make the large core, you can do the eccentricity and inclination, but you can't get the spacing right. So that's what we've played with as well. We've done, wrote a paper a couple years ago where we, you know, played with the distribution of material inside Venus, played with its total mass, the ratio of embryos to planetesimals, and its slope. And, well, for the right combination of parameters, like, sure, you can get some points approaching the red star there. But where does, like, a mass-depleted disk like that come from? And, you know, when we need to resculpt something in dynamics or planet formation, what do we turn to? Well, migration, right? So I think the solution to this, the solution to getting to kind of the right disk, comes from migration, right? There's lots of reasons to think that Earth and Venus might have gotten big enough in the gas disk phase to migrate. Talk to Steve if you want to hear some more reasons about why it's good for Earth to get, you know, north of maybe 0.5 Earth masses during the gas disk phase. Here's some high-resolution simulations during the gas disk phase that produce like 0.4 Earth mass embryos. So here's a model that Sean and I came up with. Will, you know, Earth and Venus form closer to the sun. They migrate out through this ancestite chondrite region, which is good because you want like Earth to accrete more EC material than OC that Mars did. And you can like mass deplete that region, and you can like form Mercury in isolation there and match like a whole bunch of constraints. So there's other models that do this too. This is a convergent migration model. Conclusions are up next. By Bronzendal, 2021, kind of similar idea, right? You use convergent migration. Here they have like limbi torques and co-rotation torques and heating torques in here to get convergent migration in the inner disk. And yeah, you kind of strand Mercury out there on its own, and everything else kind of moves in. So I think kind of migration is the solution there. I'll skip through this in the interest of time. But feel free to ask me about the problems that come with the giant planet instability too, because this is an extra little layer of complication on here. And I'll just kind of go to my conclusions here to wrap it up. So yeah, we still have no idea what the deal with Mercury is. the giant impact is involved in the formation, you need a whole bunch of smaller impacts. If it formed from a concentration of iron-rich planetesimals, you need to do something about, to get the orbital period spacing right. Migration, I think, is what had to have happened there. And Mercury also, as I said, it has to survive the instability. That's a big problem that is not solved yet as well. Conclusion number 2, I think we can learn stuff from exoplanets as well. We're starting to get these super Mercuries. I think if we start to learn that these Mercury analogs are common on short orbital periods, that's a feather in the cap of the orderly formation type of models. And if we start to get like lots of systems with non-uniform density distributions, maybe those problems of like reaccretion after giant impacts aren't as much of a problem. And the final conclusion, we got to land on the thing. We got to stop landing on Mars. We got to get a data point from Mercury. All right, thank you. Sorry I went over.
Yes, we got 10 minutes for discussion. Yeah.
Hi, Lauren Weiss, University of Notre Dame. Really fun talk. I'm a huge Mercury fan.
Yes.
So excited to see all this work. Coming from the exoplanets side, though, if you go back to your previous slide with the super Mercuries, the 2023 one,
yep.
This is already outdated. My PhD student, Casey Brinkman, did a thesis remeasuring masses and radii of many small hot rocky planets, including purported super Mercuries. With new mass measurements, I
saw this, yeah. I meant to put that citation in here.
Yeah, they became more Earth-like. So there might be there might not actually be that many super Mercuries out there, if any.
Yeah. And the conclusion here, I agree. And the conclusion here is we need to characterize this better, right? Because it can tell us something about Mercury.
Yeah, absolutely.
And again, maybe Mercury's a one-off. Maybe It's not related to any of this, but maybe it is, and we need to characterize more exoplanets to tell us.
Right, and so, part of my question for you is then, right, given also that these exoplanets are at orbits that are much closer to their stars than Mercury is, which in my mind kind of rules out this being solely a disk thing, right? Because how do you get the Earth composition planets at, a period of 1 day and at 365 days, but then you get Mercury composition at 88 days, right? So I guess is it okay if Mercury is just a weirdo? And if so, what does that mean for us?
I don't we have too many things in the solar system that we already try to make that argument about. And, maybe Mercury should be the last one we hold on to, because it really is a weirdo, isn't it? But yeah, I agree. It's like all this stuff super short period compared to Mercury. Like Mercury doesn't compare well to these things. And maybe when we're able to characterize, systems that are more, solar system analog, there might be something there. But yeah, I think, I'm more encouraged by if trying to look at, systems of rocky planets and trying to see if, all their uncompressed densities look the same, or if they're kind of all over the place. And if they're kind of all over the place, a lot of the holes I tried to poke in the giant impact thing, they don't bother me as much. Maybe Mercury's just our one that got smacked at the right time. Again, we're running hundreds of simulations that we're trying to whittle down to meet all these constraints, and if it's just the right impact, I can live with that.
Jack Lissauer, NASA Ames. To basically, keep you on the team, you already have your C plus average. You just need to get that D plus a little better.
Yeah.
And let's go with your strength, the A, which is why it's so dynamically excited. Well, if you had a planet between Mercury and Venus that was there, that made them connected early on, that could get tossed out, or it could smash into Venus, or it could smash into the sun. And that time scale may be longer than the time scale of these simulations. A lot of the simulations don't properly handle things when they get too close to the sun. And
sure.
That could also be just because of the integration expense. And that could also be an aspect of why you're not getting the highest velocity collisions. And also something could be thrown in from outside, as in the Jovian region, if there was some Nice model type rearrangement out there. So, I mean, Mercury, 1 in 100 or so chance that it will go unstable before the sun swallows it up by getting out to its orbit. And so something in the middle between Mercury and Venus wouldn't last, and although it could last for longer than your simulation. So
yeah, and I've done some stuff with this. It can kind of work sometimes. Again, it's like the overexcitation of the other planets that's like the biggest problem with it. But also, all our models overexcite the planets, so maybe we're missing something there too. But something you brought up that I didn't have time to mention in the talk, which is a really great point, is that like, I beat up on a lot of the old stuff done by guys like Sean and stuff, but this is a hard thing to do because of the time steps involved, right? So, studying Mercury within the full context of, the inner solar system evolution, and then trying to do, the same resolution with Mercury that's, 20 times smaller than the other planets, so you need more particles to get the same resolution on its formation. You need a smaller time step. It's not necessarily something that was readily easy to do with, the processing power 20, 25 years ago. And it's still, there are limits that we're bumping up against. And to go on to your final point, which I think I might have said on one of these here, at the bottom there, the fact that Mercury sits, the reason for the Lascar result that Mercury, 1 out of every 100 times in 5 billion years you lose it, is because it sits right there on top of this like yellow finger here, which is the, in the stability map of the nu 5 resonance with Jupiter. To me, that's not a coincidence. Like, that has to be telling us something about the orbital period problem or some of these problems. I cannot get it to work yet, but I think it's too conspicuous, and I think that's wrapped up in this whole story.
Yeah. Well, just to say what's also wrapped up is the late impact would get lighted to moon formation. And Billy Quarles and I did some dynamical studies. If people want to look at the paper, I don't want to spend time on it. But you have a non-trivial fraction, but it's smaller, well under a half, between, I think, 10 and 20%, where you get the AMD small enough, this dynamical excitation of the terrestrial planets, which, to first approximation, have their total AMD decoupled from the giants.
Yeah.
Thanks. And thank you to the speakers, the questioners, for identifying yourself. Go ahead.
Hello, Arturo Ceballos, UNLV. Maybe this is essentially the same question. I've seen some of the models you have that you form, like, oh, maybe Mercury's are too massive, or maybe you get planets where you don't want them to be. And my question is, like, is this really a problem? Couldn't it be like, since Mercury currently sits in a instability, in a stability peak that is like that it could be disrupted? Couldn't you form many Mercury analogs or very small planets close to Mercury's location and have them essentially disappear due to instability later?
So yeah, the fundamental problem with, because that's one of the first videos I showed were the 5 little Mercuries, and they're all kind of hitting it to make the point that like you can do this with smaller impacts. So if you excite the stuff here too much, right, like, which it's easy to do, the stuff that finishes and wants to be stable is like in this super stable region here, right? So if you excite junk, through this kind of mechanism too much, like you have this chain of embryos here, the stuff that survives is too far in, right? And all the other stuff gets dumped into Earth and Venus, right? Because you've excited it too much, and they're big guys there, waiting to accrete these things. So that isn't to say that it can't work or we never got it to work, but it is hard to work, and so I still think that the solution to this is wrapped up in, how those resonances got there, either giant planet instability or whatever you want to, believe about what excited the orbits of the giant planets or the residual migration phase. I think that's wrapped up in what's going on here. But yeah, that's the big problem, is that you have an extra little chain of stuff. If you get too energetic of impacts, everything's too excited. So it's the stuff way, way, way in there that survives, and everything else, goes into the other terrestrial planets.
And one last quick question from Eric.
Yeah, so Eric Geis, University of Hawaii, excellent talk. Thanks very much. I'll ask the second part of my question, which is, what is the problem with actually Earth and Venus scooping up a bit of the Mercury embryos?
I'm not saying that it isn't.
Want an EC contribution?
Yeah, I'm not saying it's a problem. I'm saying there are solid constraints that we have on late, material delivery to Earth, on that we do not want to necessarily violate, right? So it's another constraint on the problem. Yeah.
All right, let's thank our speaker for a great talk.